All right, MiniExam 5 demo. So I have already recorded this, but lost the video. So I'm just going to walk you through my answers here instead of re-recording. So for question one, the question is asking about examining the relationship between years of education and hourly wages after we control for years of work experience. So we have our X variable, our predictor variable, our Y variable, which is our outcome variable, and then we have a control variable, years of work experience. So the way I would approach this question is by looking through the different options here. So we want a control variable. So first off, we can just rule out A and D. Then second, we can see that for C, we actually don't need this interaction term, so we can rule this one out. If we wanted to go the other way and just try to construct this on our own, we could see that this would be our outcome variable, this would be our predictor variable, and then we could just use this as a control variable. So we'd set up beta 0 plus beta 1 times education plus beta 2 times experience, and then use that to predict wages. In B, we're asked, in the correct model, what does the coefficient on education represent? Well, just to think this through intuitively, we're asking how does one additional year of education relate to wages? And we're trying to control for two people who have the same work experience. So essentially this is the additional wages associated with one extra year of education after we've controlled for years of work experience, which I guess I didn't include that in the description here. So for C, why might controlling for experience change the estimated effect on education? The estimated effect of education on wages, I should say. So if you think about this, if we have two people who have 1 year different in education, that's what the beta 1 is telling us without the control. Just two people, they differ by education, in education by a little bit. How do their wages differ? When we include the control variable, now we're comparing two people with the same level of work experience, but different years of education. So what we're doing is now comparing two people with the same years of experience, where before we were just comparing everyone. So that might change the estimated effect. Okay, so that's question one. Question two, an economist is studying how coffee shop revenue differs between urban and rural locations. The variable is coded as 1 for urban and 0 for rural locations. The first part of this question asks which regression model correctly tests whether urban locations have different revenue than rural locations. So essentially we want to look at, this is essentially a 2-sample t-test question. So the way we would set this up is with a little model like this. So we have urban on the horizontal axis and revenue on the vertical axis. Urban can only take 0 and 1. And then what we're asking is there a difference in averages between these two groups? And so we could set up beta 0, which would tell us the average revenue for the 0 group. And then beta 1 on the urban variable would tell us what happens when we go from 0 to 1 with this urban variable. How does revenue change as we go from 0 to 1? That would tell us, that would be beta 1. And so we could go through the options here. I think for me, the most intuitive approach is simply to construct this on my own and then check which one of the options corresponds with my guess. But there are other ways. So you could look at this first model and see that there's a variable for urban and a variable for rural, and we actually don't need that. We just need the one variable for urban. In fact, this would give us some problems. So we can rule this out. The other is that we also don't want to interact urban and rural. That would give us some other problems. Rural just isn't required for this test. And then for D, we don't know what location is. That variable isn't defined for us, so we can rule that out immediately. Okay, so then in B, in the correct model, what does the intercept beta 0 represent? Well, I've already sort of talked this through, but the beta 0 just represents the intercept, where this model hits the vertical axis when it's at 0. And when we're at 0, that's telling us that we're not in an urban location, which means we're in a rural location. So this is the average revenue in a rural location. And that's what we have written down. So then for C, in the correct model, what does beta 1 represent? Well, again, with this nice little figure, we can see that beta 1 is just the difference in averages between urban and rural. So it's the additional revenue for urban locations. And then for D, we're just asked about a specific value for beta 1. And this just writes out what that means. Just there's $450 extra in revenue for shops in urban locations above what shops get in rural locations. Okay, so I think question 3 is maybe the hardest of all of the questions. So you've probably already sat down and tried to write this out. The way I start these kinds of questions is I'll set up the x and the y variables and then the z variables if one exists. And here we're asked about the differences in returns to advertising for brick and mortar versus online stores. So the setup here is identical to the third model in the gender wage gap example we ran through in class. So we have two different intercepts, potentially, one for the online and one for the not online groups. And then we have the possibility of two different slopes. So we've set up a baseline returns to advertising for the 0 group. And then we have this interaction term for the online group. So this tells us the additional sales for every dollar of advertisement for online stores. So in this model, what does the coefficient on advertising mean? Well, this is just the returns to sales, the additional sales for another dollar in advertising for stores that are brick and mortar. They're not online. And then for C, what does the coefficient on the interaction term advertising times online represent? Well, this is just the additional slope for online stores. So it's the additional returns to that dollar of advertising for online stores. Okay, and then part D is just a little bit too challenging. It's not very well specified, so we can skip it. We'll do similar questions a little bit later. Now, I jump back to the past and walk you through these questions live. Okay, so question 4, a researcher collected data on 200 houses and wants to understand how square foot and neighborhood affect housing prices. And then we're given a regression output, which is over here. So we have this output. So we have our coefficients, our standard errors, our p-values, and then we're told a little bit extra about what's in each one of these variables. So the first question is to interpret the coefficient on square foot. So for this one, so this is our question A. Interpret this coefficient in context. So this is square foot, and what we're asked about is predicting price. So price is in thousands of dollars. This is not log, thank goodness. So this is essentially just for every 1 unit increase in square foot, we get this many thousands of extra dollars. So this is every additional square foot is associated with 0.125K dollars extra in the price, holding everything else constant. All right, so nice. So just we move along this one direction, holding suburbs and rural areas constant, and we get this much extra in the price. So for B, interpret the coefficient on suburb. So this is for B. So this is just telling us relative to our reference category, so relative to the intercept, you get 25,000 extra dollars. So a house in the suburbs is $25,000 more expensive than in an urban area. So that's a little surprising to me, but that's what this is telling us. If we turn on a suburb relative to an urban area, then it's $25,000 extra. And then for C, we're asked what's the predicted price for a $2,000 square foot house in an urban area. So we have to actually write out a bit of a prediction here. So price is equal to our intercept, which is 85.4 plus beta 1. So this is 0.125 times square feet. So we know the square footage is going to be 2,000 plus we're asked if we're in an urban area. So this is 25.6 times 0, because we're not in the suburbs, plus negative 18.3 times 0 again, because we're not in a rural area. And then you can plug this into a calculator and this will give you a number. For the sake of time, I'm not going to do that here. So the second question is, what's the predicted price for a 2,000 square foot home in a rural neighborhood? So we're going to perform the same set of operations here. So we have price is equal to our intercept, which is our reference group, plus 0.125 times our 2,000 square foot home, plus, so it's going to be 0 because we're not in the suburbs, but it's going to be 1 if because we're in a rural area. So this is negative 18.3 times 1, because we are in a rural area. Okay, so then for question 5, a labor economist wants to test whether the return to education differs for union versus non-union workers. Which of the following models would test this hypothesis? So the way I think about these questions is I'll set up a little figure. All of them have wages on the vertical axis, and then let's have education on the horizontal axis. And we want to know if you're unionized, union, or ununion, union, are these actually different? And so the question will be whether the slopes are different. Okay, so this will be an interaction model. So let's rule out everything that's not interaction. So we can rule out these two. This leaves us with wages is equal to beta 0 plus beta 1 times education. So this would be the intercept, and then we have a slope on education. So that would match this. And then we have a second intercept term for union, and then an interaction term. So the extra returns to education for those who are unionized, which would be the slope of this line would be beta 3 plus beta 1. So this actually matches. This last one is just simply the interaction, which does a thing for us, but it's not what we're looking for. So I'm going to cross this out, and we get this one. Okay, so then for B, in the correct model, which coefficient would you examine to determine if the return to education differs by union status? Well, in this case, so let's just write out the model here. So this is beta 0. We have beta 1 is the slope for ununionized workers, the returns to education. And then here we have beta 2. So we have the extra income for those who are unionized, independent of their education status. And then we have the slope for unionized workers, which is beta 1 plus beta 3. So to test whether these two are different, we would look at beta 3. So this is just beta 3. And then for C, if that coefficient is positive, what would that tell us about the relationship? So if it were positive, it would tell us that the returns to education are higher for unionized workers. So there are a bunch of ways of saying this. I'm just going to write this one, but essentially this could be, we could say this as like every additional year of education gives you higher wages, sort of an extra amount of higher wages if you're unionized. Okay, so we have a bonus question on the back. So I'm going to rip up my carefully placed tape and we'll answer this last question. So consider the following regression output examining how temperature affects ice cream sales with month fixed effects. So we have our intercept term. So this is the baseline. And we're told a little bit here that January is the reference category for months. So we don't see January in this list, which is because it's showing up as the intercept. And then we have temperature. So this is our main relationship variable. And then sales are in dollars. So for A, why might we include month fixed effects when studying the effect of temperature on sales? Well, the reason is because a month like December has a lot of holidays. And so sales are definitely different in December than they are in January. So those 2 months are just different for reasons that are not temperature. So we would want some way of pulling out the effect of just being in December, unrelated to temperature. We could say we want to control for the factors that differ between months like January and December that aren't related to temperature. We know those 2 months are very different, even though they have very similar temperatures. Okay, so then for B, the coefficient on temperature is this number. What does this represent in the model? So this tells us that every additional increase in the units here, we're not told anything about the units of temperature, so we'll just go by degrees. We don't know whether it's Celsius, Fahrenheit, or Kelvin. So every additional increase in 1 degree is associated with a 4 1/4 increase in sales. So we could say that every increase, and we'll check yes, we have a very small p-value. Every increase in the temperature, temp by 1 degree, is associated with an increase in sales of $8.25. And then we should say holding month constant. Okay, nice. So for C, the coefficient on April is this number. Interpret this in context. So we know this number, and what this means is that April has sales that are $28 higher than in January, which is the intercept term. April has sales that are $28.4 higher, holding temperature constant. So we'd have to look at a day that's that has the same temperature in April and in January. Okay, so that's the end. This is a long one. The mini exam will not be this long, but this just gives you a bit of extra practice if you wish for that. I'll see you in the next one.